In this video, we'll be looking at assurance mechanisms and how they can help you incorporate additional design constraints in your control system. In many applications, your control system must satisfy critical constraints at all times. Violating them could mean collisions, instability, or even system failure. So, how do you ensure your controller keeps the system from violating critical constraints? Let's look at some scenarios. In an adaptive cruise control application for cars, the controller must maintain a minimum distance from the lead car. In robotic warehouses, hundreds of mobile robots carrying packages need to move around the floor while maintaining a minimum distance from each other to avoid collisions. In surgical robotics, the remote operator's commands must always result in a stable motion of the robot arm to guarantee patient safety. Now, there are some controllers such as model predictive control that allow you to encode constraints during the design. But general controllers like PID or LQR controllers do not have this intrinsic ability to handle constraints. So to manage these scenarios, today we'll be using assurance mechanisms. As you can see from the control system architecture here, the assurance mechanism sits between your controller and the plant. It helps post-process control actions to ensure that the system does not violate critical constraints due to the nominal controller's output. So, how does it work? At each sample time, the assurance mechanism evaluates the nominal control action. If it deems the control action will not make the system violate critical constraints, it passes it through unchanged. If not, it solves an optimization problem to find the closest valid action that does not violate system constraints. MathWorks provides several blocks in Simulink to implement assurance mechanisms. First, there is the constraint enforcement block for general purpose constraints. Then, there are special purpose blocks like the barrier certificate enforcement block based on control barrier functions and the passivity enforcement block to ensure energy dissipation in passive systems. You might be wondering how to choose the right assurance mechanism for your application. For that, you can use this table as a guide. The constraint enforcement block is general purpose and can be used across many domains. It allows for flexible constraint handling, for example, in robotics and autonomous systems. You can use the control barrier function based barrier certificate enforcement block when you need to keep the system states within an invariant set throughout the operation of the system, which is quite common in automotive, robotics, and healthcare applications. Lastly, the passivity enforcement block is useful when energy-based stability is critical, such as in human-robot interaction applications like exoskeletons or teleoperation. Now, let's walk through an adaptive cruise control example and see how assurance mechanisms can help enforce design constraints. The goal here is for the ego car to travel at a set velocity while maintaining a minimum distance from the lead car using longitudinal acceleration and braking. In the Simulink model, we have a plant that represents the dynamics of both the ego and the lead vehicles. The controller is a standard adaptive cruise controller which takes in inputs like the relative distance and the velocities of both vehicles and computes the desired acceleration for the ego car. Let's quickly walk through how this controller is designed. There are two modes of operation, speed control and distance control. If there is no car ahead, then the adaptive cruise controller uses the speed control loop. So the difference between the desired speed and the actual speed of the vehicle is scaled by this gain, and it adjusts how fast the car reaches the target speed. When a car is detected ahead, it then switches to distance control, where it computes a desired minimum distance using a fixed buffer plus a time gap multiplied by the current speed of the ego car. Then the gap error and the relative speed are scaled by the respective gains here, and these determine how sharply the controller reacts when the ego car gets too close to the car head. At the core of the switching is a logic block. So it checks if the spacing error, that is the desired minus the actual distance, and sees if it's greater than 0. If it's true, then the car is too close and the distance control loop is activated. Otherwise, the speed control loop is used. So this setup forms the closed loop system. For now, let's ignore the constraint block, which is disabled and acting as a pass-through. Let's run the simulation and check the results. The blue line shows the minimum distance that needs to be maintained between the vehicles, and the red line shows the actual distance. While the ego vehicle eventually matches the lead vehicle's speed, we observe a critical issue. The actual distance dips below the minimum threshold at several points, indicating dangerous behavior. One option is to fine-tune the controller to improve this performance, but oftentimes it might not be feasible. So to ensure that the ego car never violates this minimum distance, we can use control barrier functions. Let's see how. So Simulink control design provides a barrier certificate enforcement block that implements a control barrier function. You can place this between the controller and the plant to monitor the control actions in real time. And the block here works by using a quadratic programming solver or a QP solver that applies the following constraints to solve an optimization problem and find an optimal control action that is close to the nominal control action, which won't make the system violate constraints. So let's break down this math here. The second constraint that you see here is the action bound limits for the actuators. The first constraint here, let's see how we can set that up. You can pause the screen to walk through the derivation as necessary. We define the barrier function h of x, which is greater than or equal to 0, and this defines the set within which the system states should reside. And to make sure going forward the states of the system stay within the set, we need to look at the derivative of h of x. Now, this should be greater than or equal to a rising function of h of x that we show here by this alpha function. And the alpha function we chose to be gamma times h power beta. Now the derivative of h of x can be expanded out as follows, and rearranging the equations, we get the constraint equation that we see here. For our purpose, we will use the constraint subsystem here to set this block up, and we'll see how we can go about setting the control barrier function, block parameters, and the required input signals. The block needs several inputs: the nominal control action, u0, the system dynamics, f of x and g of x, and the barrier function h of x, along with its derivative with respect to the states q of x. Let's start by defining the system dynamics f of x and g of x that the barrier certificate enforcement block needs. There are different approaches you can use to determine the dynamics of the system that you're working with, like for example through system identification or linearization. But in this case, we know the system dynamics and we are going to provide the analytical equations of the system through this MATLAB function block. Within the block, we describe the system dynamics needed by the barrier certificate block using the state variables, which are the position and the velocity of the ego vehicle and the relative distance between the ego and the lead vehicle. So we can define the dynamics of the system by these state equations here, where u is the acceleration or the control input, VL is the lead vehicle's velocity. In vector form, we represent the dynamics as follows. Let us define the system constraint requirement and encode it into the barrier function using this MATLAB function block. This distance between the ego car and the lead car must always be greater than or equal to the desired minimum distance, which varies based on the vehicle's velocity, where d is the actual relative distance and d safe is the velocity dependent threshold we saw before. We can rewrite this in terms of a function h of x such that h of x is greater than or equal to 0, and this defines the invariant set, and our system state should never leave this set. And the q of x here is the partial derivative of the barrier function here over the states x. The MATLAB function block outputs this invariant set and its partial derivative. Let's now look at the block dialog. As we are setting up the block, we saw that there were 3 states, one action, and one barrier function that we are setting up. So we will enter those numbers here as follows. And the 2 main parameters that we need to set in the block dialog are the constraint factor gamma and the constraint power beta. So let's break this down and we'll start with the most important factor, gamma. You can tweak this factor to control how aggressive of a constraint enforcement you need for your application. So a higher factor means more aggressive the enforcement as the system states get closer to the boundary, and a smaller factor means a slower, much smoother response. Here we'll use a factor of 6. The constraint factor beta here by default is 1 and it works for most cases. You can use this factor to further fine-tune the control barrier function response and the vicinity of the boundary. Alright, so with that we have all the signals and the parameters that are required. We have also enabled the action bounds for the control input, so we can limit the control actions that the control barrier function block commands. Let's now run the simulation and verify if the minimum distance threshold between the vehicles are being met. The plots on the left are the previous results with the constraint enforcement disabled, and the plots on the right are with the barrier certificate enforcement enabled. We can now see that during the driving scenario where the minimum distance between the vehicles is about to be violated, the barrier certificate enforcement block steps in, solves for an optimal control input that ensures that the relative distance between the cars never drop below the minimum threshold. So you can see the modified acceleration commands during these time instances here. We can run the simulation again, but this time with a constraint factor gamma set to a smaller value. The plot on the left is the previous result where we had the gamma set to be 6, and the plot on the right is with a smaller factor of gamma. And from the acceleration commanded by the controllers, we can see that for a higher factor of gamma, you see a sharper acceleration input to enforce the constraint. So similarly, you can try this out with beta as well. And after iterating through different values for these factors, you can choose the ones that are best for your application. Now, once we have tested the control barrier function in simulation, you can generate code and deploy it onto your embedded controller to do testing on the physical hardware. So, in summary, in this video, we explored how assurance mechanisms like control barrier functions can enhance a nominal controller by enforcing critical constraints on the system. Using an adaptive cruise control example, we saw how the ego vehicle failed to maintain minimum threshold distance from the lead car with just a basic controller, and by inserting a control barrier function block, we were able to actively monitor the control actions and adjust them in real time to avoid constraint violations. If you'd like to learn more or try this in your application, please check out the links in the video description below.